Lesson 2.3, Analyzing Graphs of Functions. In this lesson, we'll interpret domain and range on a graph. We'll look at the vertical line test to verify if a graph represents a function. We'll find zeros and determine intervals for which functions increase, decrease, or are constant. And lastly, we'll identify even and odd functions. Let's start by interpreting domain and range on a graph. Let's start with domain. Domain represents all possible values on the x-axis. We read the domain from left to right. The range would be all the y-axis values, and we determine the range from bottom to top. We do these values in these orders to represent from least to greatest. Left to right on an x-axis would be the smallest numbers to the biggest numbers, and bottom to top on the y-axis, same thing, smallest to biggest. We use, or anytime there's an arrow or an open circle for our boundary, we use a parenthesis for our domain and range. Anytime you have a closed circle on your boundary, we'll use a bracket. Very similar to when we graphed solutions to inequalities back in Chapter 1. When asked to evaluate f of x on a graph, we do the same thing that we did before. Whatever the x value is, we're going to go to the x coordinate on the graph and then just determine what our y value or our output equals. Finally, when we're asked to look at zeros of functions, what we're looking for here is where it crosses the x-axis. So at what x value does the graph have an output of 0? Let's take a look at the picture down below. It says use the graph of function f to find. For part A, we're asked to find the domain of f, so the values on the x-axis from least to greatest. Looking at that kind of curved shape from left to right, I notice that it starts over here at this point. That's a closed dot, and the x value is -1. That means the smallest x value is -1 on the graph. As I go to the right, I have this open circle over here at 5. So that's the biggest x value that's going to be on the graph from left to right. To figure out our boundaries on each side, very similar to inequalities, the closed dot with the -1 is going to indicate a bracket as our boundary. But on the 5, with that open circle, we're going to use a parenthesis. Now remember, these are x values. This isn't an ordered pair. Let's see if we can determine range. Similar in fashion, but from bottom to top. The range, if we look at the lowest y value this time, that's down here at a closed dot when y is -3. That's the smallest possible output. As I look up towards the top of the y-axis, the highest output I see is +3, and that's another closed dot. Our boundaries then to represent the range, since it includes both -3 and +3, will be brackets. Next, we're asked to evaluate, determine f of -1 and f of 2. F of -1, if we go to -1 on the x-axis, we have an output of +1. So that's just the answer. It's just what y value matches with your x value. And if we go to 2 on the x-axis, 2 would drop us all the way down here to this ordered pair, and our output is -3. So instead of plugging it into a formula to evaluate, we're just locating the ordered pair on the graph. Last but not least, find any zeros of the function. Where does the function cross the x-axis? That's what we're looking for. So where does the function cross the x-axis? Oops, I think I forgot the in there. Get the little the to go. There we go. So if you look from left to right on the graph, I see that it crosses over here, and there's a second location over here. Those values are when x equals 1 and when x equals +4. That's using kind of a function on a graph to determine specific types of values. Okay, now it's your turn. Pause the video and see if you can work through these examples. Try the best you can. The more you can do independently, the easier it's going to be for your assignment and on your assessment. When you feel you've gotten through as many of A through D as possible, press play and we'll see how it went. All right, let's see how you did. This one was kind of tricky. It was kind of a tough one for you to have to try independently. I hope it went well. First, let's start with domain, letter A, the domain of f. Notice from left to right, we've got an open circle down here, and then a closed circle right there. So that's just kind of a shortened segment going from -6 on the x-axis, stopping at -2 on the x-axis. I used a parenthesis and then a bracket. And then there's a space kind of in between. And then from 2 all the way to infinity, the graph will keep continuing on. So here's where it's kind of tricky. This arrow that points down also means it's going to go to the left forever. So it's going to go to the left, and it's going to drop down. So that's going to affect both the domain and the range. For our range then, because that arrow points down, that means technically it's going towards -infinity. So that's where I started. And then if I count up on the y-axis, even though there's some gaps for x, we have values for y that go all the way up to 6. F of 0 wasn't possible. There isn't a value for the output where 0 is the input. And at -3, the output would be at -4, kind of right here in the middle right there. The 0 is kind of tricky too. Sorry about all the challenges on this one. We have 4 and then 8. So 6 is kind of right here at this point, and then 7 is somewhat in the middle between 6 and 8, obviously. So it appears that the 0 is at approximately 6.5. I hope that went well. The vertical line test is a little bit easier than interpreting all that data on the graph. So let's go with the definition. A set of points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than one point. And that would mean you wouldn't have repeating domain values, very similar to how we had our ordered pairs. In the first graph, it says use the vertical line test to determine whether each graph represents y as a function of x. Vertical lines, they're just lines that are straight up and down. If you draw a bunch of vertical lines through that sketched graph or that function, the line only crosses that graph at exactly one point, so therefore, yes, it is a function. Well, that's an it. The pen kind of got away from me there. Sorry about that. It is a function. And your drawing of the vertical lines verifies that. A circle, there's an equation for it, but a circle actually doesn't represent y as a function of x because it crosses in more than one spot. And this last one's kind of a split function. This is actually the graph of a piecewise defined function. No matter where you draw your vertical line, it only crosses in at most one place, so yes, it is a function. And that's how you use the vertical line test. Up next, we're just going to do a little bit of review with zeros of different types of functions. We've worked mostly with linear functions and quadratics, but I'm going to interpret some types of equations that we actually have done domain on earlier in the chapter. It just says set the equation equal to 0 and solve for the variable. Now this is review. This is the same kind of question as find the value for x for which f of x would equal 0. So it says find the zeros algebraically. So instead of looking at a graph to find the zeros, we're going to go back to working algebraically. Set the output equal to 0. And then we either for this one have to factor or do quadratic formula. For this one, I'm going to see if I can factor. I'm going to do a times c, and that gives us -30. Numbers that multiply to get -30, there's 1 and 30, 2 and 15, 3 and 10, 5 and 6. To get -30 when we multiply and positive 1x when we add, I'm going to do positive 6 and -5. What that means then is I'm going to split my b value into two parts. We'll have positive 6x and minus 5x. Together they add to that positive 1. And then I have minus 10 at the end. Now we've done this quite a bit, everybody. Hopefully this looks familiar once again. We put a parenthesis around the first two parts and around the second two parts. The first two, we have a 3 and an x in common, and we would have x plus 2 left over. For that second parenthesis, we need to take out the negative, and we can also take out 5 out of 5 and 10. I'm going to factor out -5 then and see what's left over. We would get x for that first part, And if we factor negative 5 out of negative 10, it goes in positive 2 times. So we have a match with our parenthesis. That means x plus 2 is one factor, and 3x minus 5 is the other factor. Solving each of these, we would have x equals negative 2 if we move 2 over. And if we add 5 and divide by 3, we would have 5/3. This solution has two values for x for which f of x equals 0. That was just kind of a quick review. We've done those more often than others. The next two are different. We've worked with domain on these, but we haven't actually graphed them or found their zeros. So let's try a couple now. G of x equals the square root of 10 minus x squared. If we start off by setting this equal to 0, just like the others, we would first need to get rid of that radical symbol. I'm simply going to square each side to do that. So that's pretty easy. But when I square 0, it stays with 0. And when I square the right-hand side, be careful here. It crosses off the square root, but doesn't do anything to the inside. It just stays 10 minus x squared. Now for us to solve this, since we're missing that bx term, we can actually add x squared to move it to the other side. And we get x squared equals 10. And now we have to square root that to get x by itself. Remember here, I'm just going to put a little star with my x. Remember here when you square root something, you put a plus and minus out in front to indicate there are two possible solutions. And 10 doesn't simplify. Therefore, the two solutions that make this function 0 out would be positive and negative square root 10. Square root 10. Okay. Last one, h of t. So now a different variable, and we have a fraction. When we dealt with fractions in domain, we focused in the denominator. But if we set this equal to 0, we're really going to focus on the numerator this time, which we haven't done so far. Here's why we can do that. If I multiply both sides by t plus 5 to get it out of the denominator, 0 times anything just stays 0. That whole thing cancels out. And on the right, we have 2t minus 3. To get t by itself, we'll add 3, and then just divide by 2. So the value for t in this function that makes the function equal 0 is t equals 3/2. At the bottom, looking at functions when they're odd or even, it says a function y equals f of x is even for each value of x in the domain. If you make the input negative, it actually just stays the same as the original function. And I'll show you how that looks algebraically, and I'll show you what that looks like on the graph as well. If a function is odd, and you change the input to the opposite sign, it actually changes the output as well. So here's what I mean. It says determine if a function is even, odd, or neither. So neither would be if you don't get the exact same answer or if you don't get a negative out in front of your answer. That would be a neither type function. For the first one, g of x equals x cubed minus x. To determine whether it's odd or even, we're going to substitute in negative x in place of positive x. If we do that on the left, we have to do that on the right as well. So what happens here is we have negative x cubed, which would be negative x times itself times itself. When you multiply a negative by itself 3 times, it stays negative. And for the second part, if it's minus negative x, that changes to plus. So this looks similar to this, but if we take out a negative from both of those terms, the x cubed would become positive and the x would become negative. So what happened on the left-hand side is we plugged in negative x, and on the right, notice we got a negative out in front. So that means this is an odd function. On the graph, it would rotate 180 degrees and equal the same thing. So it has rotational symmetry. You can't flip it left to right or top to bottom, but you could rotate it about the origin. Oops, forgot the I. There we go. Oh, there's an I in there somewhere. There it is. And then the second one, x squared plus 1 for h of x this time. If we take x and plug in negative x in its place, watch what happens when we square that. And we've had this dilemma for quite some time. When x is positive or negative, what happens to that squared? Well, if we're plugging in negative x in place of x, we do have to put that in parentheses. And we've done this many times. When we square a negative number, we get a positive output. The 1 doesn't have any change to it because 1 isn't x. Notice it's the same as the original function. So here, h of negative x is the same thing as the original function. This means it has it's an even type of symmetry, or not symmetry, it's an even type of function. On the graph, what this will do is it reflects over the y-axis. So it has reflection symmetry, or reflectional symmetry, I guess we could call it that, over the y-axis. All right, one more slide. Our final section in Lesson 2.3, using interval notation to describe increasing, decreasing, and constant functions. You read the graph from left to right. We're only going to look at x values for these solutions. On the left side of the graph, going towards the right, you'll notice the graph is decreasing. On the x-axis, it starts at -2 and ends right in the middle at 0. That means it's decreasing from -2 to 0. Constant would be if it has the same output each time. So constant is just kind of flat from left to right. From 0 to 2 on the x-axis, the graph is constant. And then as you go from 2 to 4, the graph increases. So you'll notice again, my answers are only x values. We're not looking at x's and y's. And we're also only using parentheses, no brackets. So let's see if we can apply that to these pictures down below. Feel free to add the arrows on the left side and right side for each of these. It says determine with open intervals. Again, that's going to indicate parentheses only, no brackets, on which each function is increasing, decreasing, or constant. So we're going to go from left to right. Starting over here on the left, as you go towards the right, the graph is going to be increasing. So it's increasing until it caps out right here at the top. That means I is going to be our indicator. It's increasing. Since there's that arrow on that left-hand side, we're going from negative infinity on the left until we get to -1 on the x-axis. That's when the graph increases. And then notice it changes direction from -1 on the x-axis all the way to +1 on the x-axis. It's decreasing. So from -1 on the x-axis to +1, the graph is showing outputs that decrease. From 1, though, it goes back up and changes direction to an increasing up to positive infinity. So if it's another increase, I'm just going to put a comma after the increase and say from 1 to infinity, the graph increases as well. Now you may not have all 3 of them, you may only have 1 of them, but we always read from left to right and we always only include x values. So let's see if you can try the next one. From left to right, what's happening to the graph over time? When you feel you have it, press play and we'll see how you did. From left to right, from negative infinity all the way to when x equals 0, the graph increases. But then it kind of levels off from x equals 0 to x equals 2. It has the same output each time. And then from 2 on to positive infinity, the graph will decrease over time. So that's increasing, constant, and then decreasing. For this last one's kind of tricky because it's broken up into kind of separate sections. But if we go from left to right, the graph increases and still increases and increases some more all the way to that right-hand side. So it increases the entire time. Oopsie, A there, increases the entire function. To represent that using open intervals then, we just say from negative infinity to positive infinity. So even though it increases at different amounts, it's still increasing. It's not changing direction. Whew, there we go. That's lesson 2.3. Make sure you have all of that written down and we'll do the CYU tomorrow.